them about chemistry and some stuff, and told her what we were doing just in Chem 1. And so there's a gal that she's going to be a chemistry teacher, and she's doing her observations at Emporia High School, and showed her all the things we were doing, and blew up a hydrogen balloon and a helium balloon and all this good stuff. She goes, my God, you guys are light years ahead of what Emporia students are doing in Chem 1. She goes, they do like, they don't do anything like what you guys are doing. I said, okay, well.
You know what I bet they do? Acceleration graphs. Like a bunch of
they're in
losers.
chemistry, dummy.
Oh, we're talking about Chem 1.
Yeah, you know what? Even if they were in Chem 1, I bet they're still doing acceleration graphs. That's how they.
You've never done an acceleration graph.
Yeah. The velocity time graph. If you look at it, you can tell acceleration. So.
Yeah, but
basically it's an
Oh,
acceleration.
you can calculate acceleration.
By the slope.
that was so weird. Don't ever do that again. Okay, so anyway, so here's a visual way to show significant digits. So here you've got a big beaker, right? Marks off to the nearest 10. So the best you can do is say like this is about 305. That's the best we can do. Okay, you can't go 305.0. You got 305. So here you've got one that's marked off to whole numbers of milliliters. So you can sit there and go, okay, 19.5. Okay, we can estimate the tenths place on this. Here you've got one that's marked off to the tenths, so you can estimate the hundreds. So you have varying degrees of precision. All useful, not interchangeable. So like if I'm going to measure out 1,000 milliliters of a solution for a lab, I'm not going to measure out this 100 times. I'm going to use this. But if I want to measure out, 7.50 milliliters, I'm not going to use this, I'm going to use this. So here's just a visual way. So if I take this, okay, and I add a drop to this, nothing happens, right? Theoretically, I've added a drop, but it's not going to change anything that I can measure. Now, I add a drop to this, okay, yeah, that's going to make a difference, okay, because of the fact that that's measured to the nearest tenth. Over here, I know that's going to make a difference because it's such a small measurement. So if you have large measurements and you add a small amount to it, it's not significant. That's why this is called significant digits. But if you have small measurements and you add a little bit to it, then it becomes significant because it's going to change that value. So it's just a visual way of showing.
I thought we were going
So
to blow
nothing
some stuff
happened,
up.
and
I thought we
it
were.
was going to be more exciting.
Yeah.
No, it's just to show it. Sorry.
I thought we've already went over
I know, I
that.
was
We
waiting
did, but
for
they
it.
asked why I had it here. And so
Oh,
That
what?
wasn't fun.
that's why.
I thought we were
I
blowing
was so
stuff up.
excited when I saw that, honestly. I thought we were going to do something cool today. I thought that was like some cool liquid that was going to something. Let's go back to planets.
Oh, okay, I'll see what I can do. I'll try and do something.
Yeah, because
Can we have some?
matter,
Yeah.
bro.
Yeah, planets or satellites, we don't need them. We don't need GPS.
Honestly, we really don't. Like, it doesn't really affect us, the common man.
Hunter.
But
Okay.
Tell me the last time you like broke out a map and was like, look at the map to get somewhere.
Was it easier instead of like running and jumping?
Okay, so are we going? All right. So yesterday we left off talking about this equation. Big G represents what?
no, something
6.6 times 10⁻11, 218.
AU squared.
That's 6.67 times 10 to the negative 11 Newton meter squared over kilogram squared. Otherwise known as the
Gravitational constant.
universal gravitational constant. So here's the significance of this is that, we said, hey, everything that we've ever observed, this number doesn't change. So they're on Earth, you're talking about
What
the
about
expansion.
small atomic level? Does it?
Still there.
Reasons back.
But it's just not significant enough to make a difference. Okay? So, yesterday we talked about, okay, here would be the mass of Kendra, mass of the fire extinguisher, and the distance between them. So if you were to draw a graph of distance and force, what would the graph look like?
As distance increased, the force decreased.
So as the distance gets bigger, the force is going to get
Smaller.
smaller. As the distance gets smaller, the force is going to get
Bigger.
And since it's squared, it's an inverse square. So we're going to get something like this.
Precise.
Right? Okay.
Almost precise.
So now, theoretically, this is like an asymptote. Theoretically, this force never ever drops to zero. So no matter where Kendra goes in her journeys beyond Maze High, she will always be gravitationally attracted to the fire extinguisher hanging in my room.
That was inspirational.
Well, it's not necessarily, but you know, right? So the idea of saying, oh, I'm in zero gravity, the only way you can be zero gravity is the ultimate freshman experience. Like, you are literally the only thing in the universe. Like, literally, there is nothing else. There is no Earth, there is no M&Ms, there is nothing, okay?
So
No Oreos.
eventually, is everything going to come back together, or
No,
are
right,
things-
no,
are
as a
things
matter of fact,
speeding
we're
too far
expanding,
up?
and the expansion rate is getting faster, which is a little disconcerting. So,
Will that
I
affect,
don't know why it is.
will it affect me though?
Correct.
Will it affect us though?
No,
Okay, so that's,
we're
we're good.
Now,
Future generations of children.
No worries then.
if it is, but there is an interesting idea when you look at the fact that we're sitting here having this conversation. And unfortunately, the Earth is what we, not unfortunately, but the Earth is what's known as being in the Goldilocks zone, okay? We're not too close to the sun that we're not too hot, or we're not too far from the sun that we're too cold. And we have a whole bunch of things working for us to allow us to be here having this conversation. We have a moon that has stabilized our orbit so we don't wobble. We've got two big gaseous giants, Saturn and Jupiter, basically that have our back on the outside orbit, so they sweep up a lot of meteors that could have impacted us. Our moon also creates a tide, okay, which they think has aided our evolutionary process by exchanging water, at sea levels. We have active plate tectonics, so we're always mountain building, okay, we have that going for us. So there's a whole bunch of things that just on the Earth we have going for us, which allows us to be here having this discussion. From a cosmic viewpoint, if this number had been bigger, we wouldn't be here having this discussion. Because if this gravitational constant had been bigger, after the Big Bang, the universe would have tried to expand, but it basically would have collapsed back on itself because gravity would have been too strong.
Even if it was just a fraction.
No,
Just a
there's some
significant-
tolerance, but if this number was too small, we wouldn't be here having this discussion either, because then you would have never formed the first generation of stars, okay, that would have collapsed and then produced carbon and nitrogen and all the other elements, and then you could collapse the second generation of stars. So basically the universe would have been very cold and very dark, because you would have never had any stars that would have formed. So if you look at this number, it's like, okay, well, what's the number? Well, it's kind of important that we have that number. And even if you look at like the density of the universe in terms, like after the Big Bang, it's been calculated that basically we needed 5 hydrogen atoms per cubic meter for us to be here. Because if you had more than 5 hydrogen atoms per cubic meter, it would have been too dense, it would have collapsed back on itself. If it was less than 5 per cubic meter, stars would have never formed. So there was a whole bunch of things that had to be just right for us to be sitting here in G20 on October 25th at noon and having this discussion. Because there's a whole bunch of things that could have gone bad where we're not here. Eric?
Is this the point where we do drugs?
No. No, that's up to you. That's personal. Okay. All right. That's more of the electron thing, which we'll get into later. All right. So here's the point.
Personal choice.
No. Okay. So here's the main thing that you get out of this. As the distance increases, the gravitational force becomes smaller. If you double the distance, the force becomes
4 times greater. Double.
4 times smaller.
4 times smaller, 1/4 as much.
Yeah.
Okay? If you reduce the distance by 1/3, the gravitational force increases by a factor of 9. Okay? So there's a squared relationship there, okay? There's a squared relationship. So here's what we're going to do. We're going to look at the impact that this equation has on the orbit of Mercury. So here's what we're going to do. We're going to go to the furthest point in its orbit, okay? We're going to go to the furthest point in its orbit. We're going to draw a vector pointing towards the sun of 1 centimeter long. So here's your orbit, okay? You're going to go out here to this furthest point, and you're going to draw a 1 centimeter long vector pointing towards the sun. Now, there's a common misconception that happens at this point. Everybody says, oh, the sun is pulling on Mercury. And it is, okay? Because if it wasn't, Mercury wouldn't orbit the sun. But what's Newton's third law? There's an equal and opposite reaction. So if Mercury is pulling on the sun with a relative amount of force of 1, guess what? At this point, what's Mercury doing? Mercury is pulling on the sun. Now, don't sit there and go, wow, the sun is massive. Yes, the sun is massive. Like, it's so big, like if you can obviously do this, but if you could fly a jetliner into the sun, it would take you about a month to get from the surface of the sun to the interior of the sun. Okay? It's big. There's a lot of mass in there. Okay? And the mass is continuously decreasing because we're continuously changing hydrogen into helium. But that's cool because if you don't do that, then we don't get energy from the sun because then you don't have a fusion process and that's bad.
Think about how much hydrogen.
We burn per second about, I could be wrong on this and I probably am, but I want to say it's about 5 tons per second of hydrogen is converted into energy. Okay? And don't flip out and go, oh my God, we're going to run out of fuel. Okay, the sun's been burning for about 5 billion years. We've got about another 5 billion, give or take 10 minutes, so we're fine. Okay? Round numbers.
Significant digits.
There's a significant
It's
digits.
cool how nature can never malfunction.
Oh, yes, it can.
The sun isn't ever
I will
stop
give you the platypus as an example.
Physics can never malfunction.
The platypus?
Nature.
Platypus, it's just weird.
Nature.
No, because like the gravitational
It's like
constant is
a
never not
beaver
going to be
with a duck bill.
I thought that was.
Gravitational constant is 6.
Huh?
Okay, the gravitational acceleration isn't just going to go to 2. It's always going to be 9.8.
No, what? It's
Wrong.
wrong.
Stop. Stop.
Okay, so like why doesn't the pencil
Wrong.
Okay.
shoot?
No, wrong. We'll get back to you. All right.
It's a good
So,
thought.
here's what we're going to do.
You guys are very smart though.
Now, here's what you have to understand about this. We're not saying that that is 1 Newton of force. You are not going to keep Mercury in orbit around the sun with 1 Newton of force. All we're saying is that this is the relative amount of force, and we're going to designate that as having a value of 1. So what we're going to do is figure out how much that gravitational force changes as it goes around the sun. Okay? That's what we've got going. Okay, so here's what we're going to look at. So over on that last page, let me see your lab. So what we're going to do is we're going to calculate the first relative force we're going to do together. So what we've got is 1 over d1 over d2, that quantity squared. Now, the reason that we don't worry about the F equals big G, mass of Mercury, mass of the sun, is because of the fact that on a ratio, all of that's going to cancel out anyway. So all we're finding is just the relative amount of force. So, yesterday we established what was the value of D1?
0.467.
0.467.
No, it's D2. They're not in.
D1 is 0.307.
0.307 AUs. And then we're going to divide that by 0.467 AUs. And then we're going to square that, and then we're going to take the inverse of it. So somebody take 0.307 divided by 0.467, square that number, and then take the inverse of it.
2.31.
2.31? Okay? So here's what this number means, is that when Mercury is at its closest point, the gravitational force is 2.31 times greater than what it is at its furthest point. Now, to give you an idea of how that would play out, let's just say, for the sake of argument, you make $10 an hour at your job. Your boss comes to you and says, hey, I'm going to increase your salary by a factor of 2.31. So you're going to go from $10 an hour to $23.10 an hour. So this is a hefty change. Okay? This isn't like, oh, it goes up by a little. This is a pretty massive amount of change from going from a relative value of 1 to 2.31. So all we're saying, and this is what you have to understand, we're not saying the force is now 2.31 newtons. I don't even get newtons out of this thing. What units do I even get out of this?
The lack thereof.
Yeah, I don't have any because it's AUs divided by AUs. This thing doesn't even have any units. Okay? It's just a relative value of this force. So you get 2.31. So what you're going to do is you're going to go when Mercury is at its closest point, and you're going to draw a vector pointing here of 2.31. So what we're saying is at that point, Mercury's gravitational force between Mercury and the Sun is 2.31 times greater than what it is at its furthest point. So what you're going to do is you're going to go in here and you're going to pick 2 other points. Okay? I don't care where. You're going to pick 2 other points. And you're going to do this same calculation. Okay? So the only thing that's going to change is this number up here depending upon which points you pick. So when you get done, I should be able to clearly see 4 different vectors showing this relative amount of force. A value of 1 at the furthest point, 2.31 at its closest point, and then whichever points that you pick, and show me the calculations because everybody's stuff is going to be different. So, stop that, get that done. Powerful bomb.
Yeah.
We have to even those out.
Okay, so at this point, what you should have is that you should have 4 rough vectors, relative units of force, okay? So, roughly 4. You should have 2 distinct points, one where it's going fastest, one where it's going slowest. And then you should have 1 region where it's speeding up, and 1 region where it's slowing down. And then you should have the 3 10-day periods shaded in. So you should have the 3 10-day periods, 4 rough vectors, 2 points, highest, slowest velocity, 2 regions where it's speeding up and slowing down. Everybody good with that? Fantastic. Great. Grand. Okay. Now, let's talk big picture. So, at this point, the science community is a little bit excited about this because they're going, whoa, okay, what can we do with this data? How can we weave Newton's ideas with Kepler? So here's what they did. They said, okay, let's look at this. We have F equals big G, mass of Mercury, mass of the Sun over these forces. Now, here's what I want you to look at. If, this is a huge if, Miss Treadway, if Mercury orbited in a perfectly circular orbit, would the gravitational force ever change?
No,
No. Why?
because the distance would be the same.
Yeah. We're not changing the mass of Mercury. We're not changing the mass of the Sun. We're not changing the distance. Big G is a constant. Wow, that's not going to change. There's a shock. And so the force would be the same all the way around. Okay? No worries. Simple. This I wouldn't have you guys do this because you just draw a circle and go, wow, this was kind of pointless. Okay? Everything stays the same, but it doesn't. It changes. So here's what I want to look at. When you look at this orbit, is anything up in the top going to change? No. What's the only variable going to change? Distance, right? Between Mercury and the Sun. So what we're going to look at is 2 extremes. One is closest and one is furthest. So if you look at this, when you have that bigger distance, what's going to happen to the gravitational force? What's going to happen to the gravitational force as the distance gets bigger? Okay? Small, right? So I'm going to have a small force
Got it.
with a bigger distance.
Yeah.
Right? Good?
Yeah.
Joseph, if I make the distance smaller, what's going to happen to the force? It's going to get bigger. Okay? Alright, well that's kind of cool, right? Now, we need to look at this in terms of now Kepler's second law. Kepler's second law is law of equal areas. So this is where everything comes back into one big idea. So here's what we've got. Here's the sun, here's your orbit. So at this point right here, we have the smallest distance, so we have the greatest,
Velocity.
no, we'll get velocity. Let's just talk about Newton
Force.
right now.
Force.
Greatest force. You're on step 5, I'm on step 2.
Okay.
We'll get there.
Okay.
Whoa, Kendra. Slow your mind.
So, out here, we've got the bigger distance, right? So we have the smaller force. Okay, cool, grand. All right, we got this. So now we've got to intertwine Kepler's laws. So Kendra, at this point,
Yeah.
does it have its biggest velocity or its smallest velocity?
The greatest velocity.
Greatest velocity. Oh, okay. So right here, I've got a big velocity. What about my radius? Pretty big or pretty small? Relatively.
The smaller radius.
Smaller radius. Okay? Got a small radius. Now, out here, my velocity is
Smaller.
smaller. So out here, I've got a smaller velocity. But I've got a
Big radius.
big radius. Okay. Now, is Mercury undergoing centripetal acceleration? Ellie, is Mercury undergoing centripetal acceleration?
Yes,
Yes. How do you know?
because it's going in a circle and the velocities are changing.
Yes. You could have just stopped with it's going in a circle. Okay? So, I know it has to be undergoing centripetal acceleration because it's moving in a circle. Okay, this is huge. It's moving in a circle. Because if there was no centripetal force, what would it be doing?
Going straight now.
It would be going in a straight path. So, if I stop, here's your Jedi Stoffel walk.
Oh.
If I stop the gravitational force, it's going to do what?
Go in a straight line.
Going to go in a straight line. So by virtue of the fact that it's not moving in a straight line, I know there has to be a gravitational force. Now there's three possibilities. Number one, there's a rubber band or a big string in between Mercury and the Sun. That's one option. Okay? Option number two, Mercury is traveling on an invisible track that's making it roll around. Okay? Option number three, gravity. I think let's go with gravity. I think that's a safe assumption. Okay? Could be totally radical, but I think that's the best option that we have. I might be wrong, but let's just go with this idea. Now, let's look at this equation. If gravity is causing that centripetal acceleration, and it is, how can you calculate centripetal acceleration that involves velocity and radius?
V
V
squared
squared over r. times
Centripetal force equals mv squared over r, right? Now, here's the question. Is this mass the mass of the Sun, or is this the mass of Mercury?
Total mass.
Both of them?
Question?
Ooh, tough.
Okay, is this
It might be
mass
total
the mass of Mercury, the mass of the Sun, or the combined mass of both of them? Ellie, what'd you say? Why?
Because that's what's moving.
Yeah, that's what's moving around. The Sun's pretty stationary. Okay? Right? It's kind of like swinging the rubber stopper over your head. We only contemplated the mass of the stopper.
rotating around.
No, is the sun
Okay,
rotating?
but within this, what we call the inertial frame of reference.
Does the sun rotate?
Now, here's the deal.
Are we always getting
Mass of Mercury stays constant. So this is where all of this should begin to make sense. So here's hopefully an epiphanal moment. When you're here, okay, what happens to the amount of centripetal force needed for Mercury to complete this circle? Do I need more centripetal force or less centripetal force for Mercury to slingshot around the Sun? Mr. Gilchrist?
Less.
Really?
Wait, when it's closer to the sun?
When it's closest to the sun. Do I need more centripetal force or less centripetal force?
More, because the gravity's stronger.
No. Leave gravity out of this. Only focus on this equation right there.
Because the radius is smaller.
And
Velocity is smaller. Yes.
velocity is bigger. So look, when this thing is slingshotting around here, you've got a big velocity that gets squared,
So it's
and
even
you're
bigger.
dividing it by a
Big.
Smaller radius.
smaller radius, right? So this is going to create a big centripetal force, right? A big centripetal force. Okay? Now, conveniently, what's creating this centripetal force?
Gravity.
Gravity. So when this gets closer, I need more centripetal force because of the fact that I'm moving faster with a smaller radius. But conveniently, what's happening to my gravitational force? It's also getting
Bigger.
bigger. So since gravity is creating that centripetal force, these have to go hand in hand. I can't sit here and go, well, I need more centripetal force, but gravity's getting weaker. No, you can't have the orbit. Okay? That would be like saying, hey, I want to take a turn at 100 miles an hour, but I'm going to put, ice down on the track. No, it won't work. No, it would be bad.
If you didn't flip and there's no one around you.
So,
Yeah, you're just.
Yeah, really.
is that the sound that you make too?
Yeah.
Okay. So this is one of the big epiphanal moments in science, because it's sitting there going, wow, this is cool. I need more centripetal force, and gravity is providing a greater centripetal force because I'm moving faster with a smaller radius. My gravitational force is getting bigger because I'm dividing by a smaller distance. Now, out here, what happens? Do you need as much centripetal force? No. Why?
Big radius.
Radius is bigger and
Velocity is smaller.
velocity is smaller. So out here I've got a smaller velocity dividing by a bigger radius, so therefore I don't need as much centripetal force, but conveniently gravity is getting weaker because there's a greater distance between them. Okay? So now, if Mercury was orbiting in a perfectly circular orbit, would my centripetal force ever change? No, because the velocity would never change and my radius would never change. So since my centripetal force would never change, guess what? I don't need to change our gravitational field. So here's what's important. Don't sit there and go, oh, gravity is the same. No, it's not. Gravity changes throughout this orbit. Stronger when it's closer, further when it's, or weaker when it's further away. Okay? So gravity is not the same. It changes a lot. Now, at this point, let me see the paper. You should be able to finish this up when you get down to questions 4 and 5. So on number 4, you want to calculate the gravitational force between the Mercury and the Sun and that radius. Now, I was nice and I gave you the radius in meters. On number 5, you're going to calculate the centripetal force needed to keep Mercury in orbit, and we're just going to assume for the sake of argument that it is a circular orbit, because otherwise you got to do calculus and a whole bunch of weird stuff. So we're just going to assume that it is a circular orbit. So, and I tell you, use mass 4 pi squared r over t squared. Pay attention to the units. So what the first thing that you're going to do, you know why I don't teach freshman?
You told us.
Because of people like you.
Ow.
That's my job.
Which one was that?
Okay. Quit. Okay. That's the most random thing. Okay, so on number 4, we're just going to make the assumption that the distance between Mercury and the Sun stays constant, and then we're going to assume that it actually assumes a perfectly circular orbit, which on average it is. It's actually elliptical, but on average it's circular if you kind of level things out. And then on number 6, you can compare your answers to 4 and 5. When you get done, I don't want the data table, okay? I know what the data is. So when you get done, staple your graph to the back, make sure everything's labeled on it. There we go.
That's the last thing we're doing today?
Oh no, you won't have any homework tonight.
What's
2 nights in a row.
kind of slang robot?
One day has
I mean,
to
that sounds like anyway, he's still cutting.
It's not recording. It really is recording though. It is? Yeah, I have it recording.
I thought it was like a Star Trek joke, like Scotty from
What
Star
else
Trek.
can we do?
Let's
go back.
The future, like you traveled into the, you know.
We can do these.
You didn't say the 88 stamps?
Ooh, those are colorful.
So, where'd you give me that for? I haven't done that yet. Or it'd be on my paper. Oh, I thought what? So, as radius gets smaller, velocity.
Ooh, 3, 2, 1.
That was just a hard concept for me.
I think we should start off every show like that. Every show.
Find it.
Oh, you can also draw.
So, mass is.
This is such a pretty picture. This is gonna be a good clip to watch. Ready? We gotta end it. What should we end it with? That one?
Yesterday was a good day to miss.
Oh, that was a good one. Let's end it like that.
Burkham's a dope like
I don't have blonde hair.
Thick blonde hair.
Okay. I'll have to watch this.
Yeah. You'll have to see what happens.
Okay. Okay. So now that we've kind of got an idea of what's going to happen, so we're going to go through, we're going to drive kind of 3 big equations and see how they work. We're also going to view it from like a historical perspective. So here's the deal. So let's say that, not to scale, but Kendra is standing on top of the Earth, okay? And we want to find the gravitational attraction between Kendra and the Earth, okay? So there's 2 ways that we could do this, okay? Option number 1, we're going to use this equation that F equals big G, okay, and then distance squared. So we're going to take a single proton in a carbon atom in a strand of DNA at the end of Kendra's left index finger. Okay? Single proton. And that single proton is gravitationally attracted to every point, every proton, every neutron, and every electron that makes up the Earth. So we're going to take that single proton, right? So this is going to be the mass of that one proton. And then we're going to go through and we're going to do this calculation separately for every proton, neutron, and electron that makes up the entire Earth. So we've got to know all of these masses, which we're only dealing with protons, electrons, and neutrons, so there isn't much variance. But the hard part is going to be the distances, okay? So we're going to do that calculation with that one carbon proton. Now, carbon has how many protons? Each carbon atom has how many protons? 6. So then we're going to do that. Once we get done with that, then we're going to do the same set of calculations with the second proton in that nucleus. And then the third, and then the fourth, and then the fifth, and then the sixth. Then we're going to do that with all the electrons. Then we're going to do that with all the neutrons. That's in one carbon atom. Then we're going to move to the nitrogen atom that is also making up that strand of DNA. We'll do the same thing again and again and again and again and again and again and again. Oh yeah, we'll be long gone. Okay? Our carbon will be part of the universe before we're done. So this is going to be a long and arduous process. Okay? And it's going to be brutal. But in reality, that's what's happening. So when you're standing here on this rock, every particle that makes you up, every electron, every proton, every neutron, is attracted to every electron, proton, and neutron that makes up the Earth. Okay? This is the reality of it. So everything that has mass has its own gravitational field. But now, let's just think. Is that one proton going to be more attracted to the stuff that's closer or more attracted to the stuff that's further away? closer, right? Because it's a smaller distance. So as we shift this gradient down, the gravitational force is going to get weaker and weaker and weaker and weaker and weaker. And we have to know where everything is located, and it's just going to be, we can't do it. I mean, that's just the reality. We can't do it this way. But in reality, that's what's happening. So what we're going to do is we're going to treat Kendra and the Earth as what we call a point mass. Okay? The beauty of point masses is that instead of doing all these calculations, what we're going to do is we're going to treat Kendra like she is condensed to a single point of mass. Okay? Like we're going to squish Kendra together until she's like this. Okay? Then we're going to take the Earth and we're going to do the same thing. We're going to take the Earth and we're going to compress the Earth until it's a single point mass. So basically what we're going to do, instead of doing all of this, we're going to say that there's Kendra, there's the Earth. 2 points. Kendra's mass is still 50 kilograms. Mass of Kendra. Here's the mass of the Earth. Still 5.979 times 10 to the 24th kilograms. And assuming that Kendra is standing on the surface of the Earth, and not on the top of Mount Everest or out in orbit, and these 2 points are separated by 3.713 times 10 to the 6th meters. So once we do this, then it becomes like finding the attraction between Kendra and the fire extinguisher. Kendra's mass, the fire extinguisher's mass, we plug in the numbers. So at this point, we're going to go F equals, now, don't want to touch a calculator, don't even breathe on a calculator. Okay? Don't touch a calculator, step away from the calculator. So this is going to be, this force is going to be 6.67 times 10 to the negative 11th newtons meters squared over kilograms squared times the mass of Kendra, 50 kilograms, times 5.979 times 10 to the 24th kilograms, divided by 6.3713 times 10 to the 6th meters squared. Now, what I want to do is, I want to look at this from what we call an order of magnitude. All I want to do is get an idea of what the exponent should be. Okay? Because trust me, trust me, trust me. If you don't square, cube, keep track of the exponents, you are going to get answers that make absolutely no sense. Like my AP Physics students just did similar type calculations. One of the things you're going to calculate is how long it takes the Lunar Command Module in the Apollo missions to orbit all the way around the moon. That's going to take a while, right? But they dinked up the conversions and they got 0.2 seconds as the time it takes from the Lunar Command Module to orbit all the way around. 0.2 seconds. You can't snap your fingers in 0.2 seconds. Okay? Now, the other good one I got, this is a couple years ago.
Wait, you said you can't snap your fingers that?
No, it takes less.
0.2?
No.
Then why can't I do a stopwatch that fast? Oh, because I'm a beast.
What? That's different than snapping your fingers.
Okay, you don't go there.
You stop watching right now. Prove this.
No. Now, the other good one I got, and I did this conversion. They did the calculation for how long it takes for the Lunar Command Module to orbit. It was literally longer than the universe itself has existed. Okay, literally. It was more than 14 billion years. But this is what the calculator said, and that's what they wrote down. So you have to be aware when you get these answers to look at this and go, oh, does that make sense? Because you're dealing with velocities and time periods of stuff that you're not used to dealing with. So this is why it's handy just to do an order of magnitude. So the only thing we're going to worry about is exponents. So look at this. I got 50, which is 5.0 times 10 to the first. So I take 10 to the first, multiply that by 10 to the negative 11th, I get 10 to the negative 10th, right? I take 10 to the negative 10th times 10 to the 24th, that gets me 10 to the 14th. So up on top, I've got 10 to the 14th. Okay? Just an order of magnitude, that's all it is. Now, down here I've got 10 to the 6th, and I'm going to square that. So when I square 10 to the 6th, I get 10 to the 12th. So I got 10 to the 14th divided by 10 to the 12th gets me
10 squared.
10 to the 2nd, right? So subtract your exponents, I get 10 to the 2nd. So this gives me some idea of what the magnitude of this force is going to be. It might, depending upon how the actual numbers flush out, I might be at 10 to the 3rd, I might be at 10 to the 1st. That's about as much variance as I'm going to have. So if I do this calculation and I get 10 to the 6th, oh, I have done something very, very wrong. Or if I do this calculation and I get 10 to the negative 8th, I have done something horribly, horribly wrong. Okay? So, if you're not sure if you're right when you get an answer, just look at the order of magnitude. Make sure that you've squared stuff. Eventually, we're going to be dealing with radius cubed. Okay? That really makes a difference if you forget to cube a radius that's 10 to the 6th, because 10 to the 6th cubed is going to be 10 to the 18th. So, 10 to the 6th versus 10 to the 18th, you're talking a difference of basically 100 million. In terms of an order of magnitude. So the calculations themselves aren't going to be horribly difficult, but what you will screw up is the small stuff. Okay? Now, somebody take your, I'd prefer a whole bunch of you, take your calculator and let me know what you get out of this.
Times 50.
And if you're not sure if you're good with a calculator, this would be a good time to check.
From Picasso with that.
That's 3713.
The only numbers that you need that's different, that's not on your equation sheet, is this 50 kilograms. Big G is there, the mass of the Earth is there, the radius of the Earth is there.
Should we save the?
What is that radius? 6.3713.
13 times 10 to the 6 meters. That's why I said store this, store big G, store the mass of the Earth. Store these three variables, the radius, the mass, and big G. By the way, my high school physics teacher was a jerk and wouldn't let us use calculators on tests, so I had to do this by hand. I was in your shoes.
What?
It sucked.
How do you do that by hand?
I got
You got very good at mental math.
I got 491.
491.
I did too. I didn't know if that was correct.
That's also what
I waited until
I
waited until somebody else was like every time. Unless I'm like 100% sure I did it and I calculated it correctly, I'm just like, no, I was sitting there, I was like, okay, I just need to pause so I don't, you know.
Wrong.
Okay, should be about, this is what it should be.
No, you're the puppet.
Okay? Now, pretend that you don't know anything about this. Okay? You don't know anything about this entire screen, which is going to be easier for some of you. Okay? And let's pretend that you're back on that very first day that you were in this class. The very first day. And we took the springs, right? And we suspended like a 1 kilogram mass, and I said, okay, to get the gravitational pull on a 1 kilogram mass, what did I tell you to do? Take 1 kilogram times.
The gravitational acceleration.
Did you say times gravity?
I said gravitational. I finished it.
Okay, thank you very much. So you took 1 kilogram times G, and you got 9.8 liters, right? And you're all going, at the time you're going, I flip it out, but wow, why does this work? Wow, okay, this is why this works.
So you should do that times 50.
So, imagine that we're going to suspend Kendra from the spring.
Oh my gosh.
We're not. I said,
First we're squishing me, and now we're putting me on a string.
so, now I'm going to take Kendra, and so somebody take 50 kilograms times G. What do you get?
490.
490.
Pretty freaking close.
Yeah, basically it's the same number. So here's the question. Why aren't they the same?
Because that's how it's supposed to be.
Why?
The relationship
That's
that
the
they have.
gravitational pull. That's the
Yes.
force that the
So the sum total of treating Kendra as a point mass and the Earth as a point mass is 490 newtons. her mass times the gravitational acceleration is 490. So imagine this, on the very first day you all would have flipped out. I said, okay, to find the gravitational pull on a 1 kilogram mass, you're going to take 6.67 times 10 to the negative 11th times 1 kilogram times the mass of the Earth, 5.979 times 10 to the 24th, and then you're going to divide it by that number squared. You all would have flipped out. Okay?
I'll drop the class.
Yeah, it's like, oh, screw this, I'm out of here. So, but if I had said, hey, just take 50 kilograms times 9.8 meters per second, okay, hey.
He said he said.
Oh yeah, if I would have said that, everyone would have known I would have said that.
Yes. So, here's what's important. The two numbers are the same. Okay, we will finish this up tomorrow.
Wait a second.